Dear students, welcome to physics class. Today in this video lecture, we will discuss electric field intensity at any point on the axis of a uniformly charged ring. So in this case, we have a ring and that ring is uniformly charged, means there is an equal charge at everywhere on the surface of the ring. Let A is the radius of the ring and we want to find electric field at P point due to this ring. To find the electric field at P point, we will divide the ring in small portion. Firstly, we will take one small portion and we will find the electric field at P point due to that small portion. After that, we will take another small portion that is opposite to this small portion, diametrically opposite to this small portion. Let it is AB, another one is CD. So one by one we will find the electric field at P point due to this opposite diametrically end, and we will see what will the result come. Similarly, we will take one portion and other portion is opposite to that portion. So in that we will take different part, different portion, and we will find the electric field at P point. At the end, we will add all the electric field which is produced by this small electric charge element. Okay, so one by one we will do that. But here we will discuss only two portion and rest of the portion we will add like similarly. Okay, so let's start doing that. How to draw the electric field line. So electric field line, firstly we will assume here, let us a very small portion AB. This portion we will take, this is bigger, actually the pieces are very small. So let that length is dl. And let the charge on it is dq. On the small portion, let the charge is dq, and the name of this portion is AB having a length dl and charge is dq. And let the total charge on the surface is, the total charge is q. The total charge on the whole ring is q. Okay, so now we have to find the electric field at P point due to this small charge element AB. So we will draw electric field line because the portion is very small, so electric field line produced by this charge will be very small. So we'll draw a very small electric field line, that is DE. So let us consider this angle is theta, and we will draw a perpendicular y-axis here. So now if this angle is theta and if we extend this length also, x-axis, if we extend x-axis and the y-axis, so this angle will also theta, that is vertically opposite angle. Now we will resolve this DE component in two parts. This side the component will be DE cos theta, and toward this side the component is DE sin theta. So this is the two component of the electric field DE which is produced by this element of length AB. Okay, similarly we will take another element. Let the length of that element is DL, again the same length element, and we will take that element at that diametrically opposite. So again the length is DL and it will produce a electric field at P point. So we'll draw the electric field at P point. Okay, so let's start. We will drawing here. This is the electric field DE produced by CD element, DE electric field, because both elements are diametrically opposite and both will produce the same electric field because distance is same. So DE field is produced by CD element, and this angle again theta, So vertical opposite, you can write this one as theta. And now resolve the DE component. So we'll resolve the DE electric field in two parts. So one portion will come toward this side. This will be your DE cos theta, and the other portion will come toward this side, that is your DE sin theta. Okay, so now all the vertical component, if you see all the vertical component, first one is DE sin theta and DE sin theta, both are equal and opposite, and when both are equal and opposite, so what will happen, they will cancel out each other. So there is no contribution of electric field due to this DE sin theta element. Similarly, there will be so many vertically or diametrically opposite element will be there. They will produce the field and the component will resolve. So every time DE sin theta component will cancel out. So there will be so many DE sin theta component, and we will take summation of all the DE sin theta component, and they all will be 0. So you can write DE sin theta, and the net field at P point will be due to this DE cos theta, this because of these two components only for these two elements. Like that, there are so many elements, so the net electric field will be due to the summation of all electric field component along x-axis having cos theta with them. So electric field intensity, resultant electric field intensity will be due to these components. So now we will calculate the value of the net electric field. So before proceeding that, you can see here, let us consider charge on unit length. If total charge on the sphere, this ring, sorry, it's a ring not sphere, the total charge on the ring is Q, and what is the circumference or length of the ring? That is 2 pi a. So charge on unit length, so it will be Q by 2 pi a. The next is charge on the element ABs. What will the charge on this element? If we want to find the charge on this element, that we have considered dq. So that charge will be equal to charge per unit length, that is q by 2 pi a. And what is the length of this AB portion? The length is dl. So dq charge will equal to charge on unit length multiplied by dl. Now electric field intensity at P due to the charge element AB. So we have to find electric field intensity due to this element at point P. So we will write the electric field formula, that is 1 by 4 pi epsilon naught dq, and the distance, this one, distance between this element and P. If this one is r, a, so what will be that distance? R square plus a square and the root of that. So we will get r square plus a square. This is the distance, square and root will cancel out with each other. So this is your equation number 1. Similarly, if you want to calculate the electric field at P point due to CD element, so that will be also same. Due to CD element, you will get the same expression because distance is same. Let it be d dash, de dash. So what will you get? 1 by 4 pi epsilon naught. Again, what is the distance of P and this point? This is also r square plus a square. So the same distance is there, r square plus a square, and this is equation 2. So from 1 and 2, you can say dE and dE dash is equal to dE, and if you want to represent like that, so you can replace here dE dash and here 1 dE dash cos theta, dE dash. Okay, and both are equal and opposite, so all the component will be 0, and E net is equal to dE cos theta will come. Now the next step is we will substitute the value of dE and cos theta. So we will take the value of dE because all these twos are equal. So we will substitute the value of dE here and cos theta value here. So we will get the net electric field. So E net is equal to summation of dE cos theta. And what is your dE? dE is 1 by 4 pi epsilon naught dq charge and r square plus a square. Now we have to substitute the value of cos theta. So what will be cos theta? If you see the previous diagram, you can find the value of cos theta from here. Base by hypotenuse. So we'll substitute this value. Base is your r, and hypotenuse is r square plus a square unroot. Unroot you can write 1 by 2. Now we have to solve this one. We will substitute the value of dq. Earlier we have derived dq is equal to q by 2 pi a dl. This is the value of dq. You can see in the previous in the starting of this we derived the value of dq. So we will substitute this value of dq, that is q dl by 2 pi a, and here 1 and 1 by 2. So we will add the powers r square, a square and 3 by 2. This is your r. Alright. So now we will take out the constant terms from the summation. We know 1 by 4 pi epsilon naught is a constant. We can take it outside. Q charge is constant. Distance r is also constant. 2 pi a, the length of ring is constant. So all these distances are constant. We will write all the thing outside the summation. So what thing is not constant? DL. Why DL is not constant? What is DL? DL is the length of this element. So we divided the whole ring into small length, that is DL. So if we add all the small length ring DL, so DL plus DL plus DL, what will you get? You will get the length of whole ring, that is 2 pi a. So we can write summation of DL is equal to 2 pi a. So this is your final expression which you will get 2 pi a r square plus a square 3 by 2, and summation of DL is, we will add all the small elements and that elements will be equal to 2 pi a. So this is the final expression for E net, resultant electric field. Now we will discuss some special cases. The first special case is when P lie at the center of loop. We have a one loop, one ring. If this P point where we want to find the electric field, if this P point is at the center of loop, so this distance r will be 0. If P point is not there, the P point is at center, so in that case your r equal to 0. Now substitute r equal to 0 in the star equation, you will get E is equal to 0. Now the next case is when r is very greater than a. In that case your P point is very far as compared to this ring radius. So in that case you can neglect r. Your P point is very far. So in that case you can neglect a. So in this equation when you are neglecting a, what will you get? You can put a equal to 0. So finally you will get this expression r q, and this expression is similar to the expression of a electric field at a point. So when, what is the condition when electric field at P point can behave like a point charge? So in that case you will substitute this condition. So now you can say we have proved here, you can say a circular loop of charge behave as a point charge when the observation point P is at very large distance from the loop. This loop is behaving like a point charge. When this condition is there, and you will get the electric field due to the point charge. So this topic is over. Thank you, students.